All right. Today, we're going to take an incredible journey deep inside your own body. We're going to meet the unsung hero of your nervous system, the tiny little cell that makes literally everything you think, feel, and do possible. Yep, we're talking about the neuron. I mean, seriously, have you ever stopped to think about it? You see a ball flying towards you and bam, almost instantly your hand is up to catch it. Or you just decide, hey, I'm going to move my finger, and it just moves. How does that even happen? How does a message get from your brain all the way to your hand so unbelievably fast? Well, it all comes down to this one incredible cell. The neuron is basically the fiber optic cable of your body's information superhighway. So in this explainer, we're going to do something cool. We're going to follow the path of a single message as it zips down one of these amazing messengers. So our journey kicks off right here, with section 1, receiving the message. You got to think of this first part as the neuron's own personal set of antennas, and they are constantly listening for signals. And what are these antennas? Well, they're called dendrites. Their name actually comes from the Greek word for tree, which makes perfect sense because they look a lot like tree branches, right? And that shape isn't an accident. It's designed to give them as much surface area as possible so they can pick up signals from literally thousands of other neurons all at once. So the dendrites' job is pretty straightforward. They just have to listen. They act like these super sensitive antennas. They collect all this incoming chatter, and then they funnel all of it down towards the neuron's command center to be sorted out. Okay, so the message is in. What's next? Well, now we're at the neuron's command center. The message gets sent to headquarters, where a really, really important decision has to be made. Do we pass this thing on or not? Welcome to the soma. You can also just call it the cell body. Look, if the dendrites are the antennas, then the soma is the central computer. It's not just the core of the neuron, it's the brain of the whole operation. It keeps the cell alive and makes sure everything's running smoothly. Right inside the soma, you've got the nucleus. That contains all the genetic blueprints. But for our purposes, its main job is to integrate, basically to add up all the different signals it's getting from all those dendrites. And then it makes the big decision. Is this message important enough to send forward? It's a critical go or no-go moment. Now, if the decision is go, well, hold on tight, because the signal gets fired off down this remarkable biological highway, and this is where things get fast, like really fast. This highway is called the axon. It's this long, cable-like fiber that stretches away from the cell body. And, some axons are super tiny, but others can be incredibly long. I'm talking about the ones that run from your spine all the way down to your big toe. Its one and only job is to get that electrical impulse from point A to point B, no matter the distance. And not just begs the question, right? If this is just a biological cable, what's the secret sauce? How does it get that message across so fast without it fizzling out or slowing down, especially over those really long distances? Well, the answer is this absolutely brilliant piece of biological engineering called the myelin sheath. It's a fatty layer that's wrapped around the axon, and it acts like a super-powered insulator. And believe me, this isn't just a minor upgrade. This is a total game changer for signal speed. So how does it work its magic? Well, the myelin acts just like the rubber insulation on an electrical cord, It stops the signal from leaking out. It's actually built by these amazing little helper cells, like Schwann cells. And this insulation allows the signal to literally jump from one gap in the sheath to the next, which is way, way faster than just flowing straight through. And this little chart just shows you the difference perfectly. With that myelin sheath, the signal is super fast, it's highly efficient, and it stays strong and clear the whole way. Without it, much slower, less efficient, and the signal can get weaker over distance. It's basically the difference between fiber optic internet and, well, old school dial-up. So just how fast are we talking about here? Get this. Some of these myelinated nerve signals can travel at speeds up to 268 miles per hour. That is faster than a Formula One race car, and that is how you're able to react to something in a split second. So, our signal has just blazed down the axon at incredible speed. Now it's reached the end of the line, but its journey's not over yet. It has to pass the baton, so to speak, to the next neuron waiting in the chain. And this final handoff happens at the axon terminals. These are just the small branches at the very, very end of the axon. They're the transmitters. They get the message all packaged up and ready to be sent across to the next cell. So here we are. The electrical impulse made it. It's at the absolute edge of the neuron. But now we have a problem.
There's this tiny, tiny gap between this neuron and the next one, and an electrical signal can't just jump across empty space. So now what? And this is where the real magic happens. To get across that gap, the message has to change its form. The electrical signal triggers the release of these tiny chemical messengers. You've probably heard of them. They're called neurotransmitters. These little chemicals shoot across that microscopic gap, which is called a synapse, and they're caught by the dendrites of the next neuron, kind of like a key fitting perfectly into a lock. And that chemical signal, it ignites a brand new electrical signal in the next cell, and the whole incredible process starts all over again. So let's just zoom out and put it all together. The whole journey is basically 4 simple steps. Number 1, the dendrites receive the message. 2, the soma processes it and makes a decision. 3, the axon transmits it at crazy high speed. And 4, the axon terminals send it on to the next guy. Receive, process, transmit, send. That's the life of a signal right there. You see, what we've just followed is the journey through one single neuron. But it is so important to remember that this one cell isn't working alone, not even close. It is one tiny but absolutely vital link in a mind-bogglingly huge network. How huge? Well, the average human brain has an estimated 86 billion neurons. I mean, that's more than 10 times the number of people on planet Earth. And every single one of them is forming connections with thousands of others, creating a network so complex it's hard to even imagine. You know, as the neuroscientist Jean-Pierre Changu once said, this incredible machine of interconnected neurons is what accounts for everything that makes us, well, us. Our actions, our beliefs, our passions. It all starts with this simple little electrical and chemical signal we've been following. So, I guess I'll just leave you with this final thought. We've seen how one single neuron works, kind of like a single high-speed wire. But what does it even mean to have 86 billion of those wires all firing and talking to each other in perfect harmony just to create a single thought or a memory or even your sense of who you are? It's the most powerful information network ever created, and it's all happening right inside your head.